Modern concrete is everywhere. It holds up our bridges, our tunnels, our apartment blocks, our dams, our ports. It is one of the materials that makes the modern world feel solid, and yet modern concrete has a quiet enemy: time. Water gets in, salt gets in, tiny cracks become larger cracks, steel reinforcement begins to corrode. The repair work starts. Then the repair work needs repair. Now compare that with parts of the Roman world. Ancient harbor structures battered by seawater, massive walls still standing, vaults and monuments that survived earthquakes, weather, war, neglect, and centuries of being misunderstood. The easy version of the story says the Romans had a secret recipe, but the better version is stranger, because Roman concrete was not one recipe. It was a material system: ash, lime, stone, water, heat, local geology, human habit, and time. The Romans did not make magical concrete, but in some places they made concrete that behaved like it was still alive. The wrong question is, was Roman concrete better than modern concrete? That question is too broad. Modern concrete is not a failure. It builds at a speed and scale the ancient world could not imagine. Modern engineers can calculate loads, reinforce structures with steel, pour enormous foundations, and build upward into the sky. Rome could not do that. So this is not a story about modern engineers being foolish. It is a story about different materials solving different problems. Modern concrete often optimizes for speed, standardization, compressive strength, steel reinforcement, and predictable performance. Roman builders were working with different tools, different supply chains, different labor systems, and different expectations. They were not trying to build a skyscraper. They were building harbors, baths, walls, vaults, roads, warehouses, temples, and cities. And in some of those settings, especially where volcanic materials were available, Roman builders created concrete that endured with a patience modern materials scientists now study carefully. That is the real question, not whether Roman concrete was always superior, but why some Roman concrete survived so well in conditions that normally destroy. The first clue is ash, not ordinary ash from a fireplace. Volcanic ash. Roman builders learned that certain volcanic materials could change the behavior of lime-based mortar. One famous source was around Pozzuoli near Naples, which gives us the word pozzolanic. When volcanic ash reacts with lime and water, it can form durable binding compounds. That sounds technical, but the basic idea is simple. The ash was not just filler. It was active. It helped the material become something tougher than a simple lime mixture. This is where the landscape becomes technology. The Roman builder did not invent the volcano, but Roman builders learned how to use what the volcano left behind. That kind of knowledge is easy to underestimate because it does not look like a machine. No gears, no wires, no bronze dial, just powder, lime, water, stone, and experience. But the intelligence is there. It is in knowing which ash works, which sand fails, which mixture sets, which wall holds, which harbor resists the sea. The recipe begins in geology, but it becomes technology only when people learn how to use it. Seawater is supposed to be the enemy. It moves constantly. It carries salts. It enters cracks. It attacks metal reinforcement in modern concrete. It turns small weaknesses into expensive failures. That is why Roman marine concrete is so interesting. In some ancient harbor structures, seawater did not simply destroy the material. It appears to have helped drive long-term mineral growth inside it. The water kept interacting with the concrete. The chemistry did not stop when the builders left. It kept going, slowly, quietly, for centuries. That does not mean every Roman harbor was indestructible. Many ancient structures failed, many were repaired, many disappeared completely. Survival bias matters. We are looking at what lasted, not everything that was built. But the surviving marine structures are still remarkable because they show a material behaving differently from what we expect. Modern concrete often tries to resist the environment. Some Roman marine concrete seems to have recruited the environment. The sea became part of the story, not just a threat, a participant. For a long time, the white chunks found inside some Roman concrete looked like mistakes. They are called lime clasts. To a modern eye, they can look like evidence of sloppy mixing, as if the ancient builders failed to blend the material properly. That interpretation is tempting because it flatters modern precision. We see irregularity and assume error, but newer research from MIT and collaborators suggested something more interesting. Those lime clasts may have been part of the durability mechanism. The idea is careful. Not magic, not instant healing, not every crack in every Roman wall closing like a wound in a superhero movie. The idea is that when small cracks form and water enters, reactive lime can dissolve, move through the crack, and recrystallize as calcium carbonate. That process can help fill small cracks before they grow. So the supposed flaw may have had a job. This is the kind of reversal that makes ancient materials so powerful. The object does not change. Our interpretation changes. What looked like poor workmanship becomes evidence of a different construction logic. Not less intelligent, just less modern. The next clue is process. Materials remember how they were made. The same ingredients can behave differently depending on sequence, heat, water, timing, and mixing. In Roman concrete research, one key idea is hot mixing. Instead of first slaking lime into a paste and then mixing it cold, Roman builders may have used quicklime in a way that generated heat inside the mixture. That heat matters. It can change the chemistry. It can help create those reactive lime clasts. It can produce a material with different internal structure. This is not a secret spell. It is process knowledge. Think of cooking. The same ingredients can become completely different foods depending on when heat is applied. Concrete is not food, obviously, but the principle holds. Sequence matters, heat matters, timing matters. What the Romans may have understood through practice, modern researchers can now test through chemistry, microscopy, and experimental mixes. That is the bridge between ancient craft and modern science. The Romans did not need our equations to make the material. We need our instruments to fully explain why it worked. One reason this story keeps developing is that archaeology keeps finding better context. Finished buildings are useful. Ruins are useful. But an unfinished construction site is a different kind of gift. At Pompeii, researchers studied a construction site frozen in time by the eruption of Vesuvius in 79 CE. Instead of only seeing completed walls, they could examine traces of process, materials, piles, mixing evidence, and work interrupted before it became invisible inside a finished structure. That matters because process is usually the thing archaeology loses. We find the wall. We do not always find the moment of making. We find the result, not the workflow. Pompeii helps because the disaster froze ordinary work mid-action. It gives researchers a rare chance to ask not just what Roman builders used, but how they used it. That is why the Pompeii evidence is so valuable for the hot mixing story. It connects chemistry to a real construction setting, not just a lab sample, not just a surviving monument. A worksite, human labor stopped in the middle of becoming architecture. If Roman concrete was so impressive, why did people stop using it? This is another place where the simple answer is wrong. Technologies do not vanish only because people forget one sentence. They vanish when systems change. The Roman concrete tradition depended on materials, labor, transport, building culture, recipes, apprenticeship, local geology, and institutional demand. When the empire changed, those systems changed too. Maybe the right ash was no longer moved in the same way. Maybe the workshops changed. Maybe construction priorities changed. Maybe later builders used different binders because they solved different problems. And much later, modern Portland cement became dominant because it was powerful, fast, standardized, and suited to industrial construction. So the Roman recipe was not lost like a password under a floorboard. It was lost like a language loses speakers. The words may survive in fragments. The grammar fades when people stop using it every day. Modern researchers are not studying Roman concrete because ruins are romantic. They are studying it because the stakes are practical. Concrete is one of the most widely used materials on Earth. It is also tied to enormous emissions, resource use, and repair costs. If concrete lasts longer, cracks less, repairs itself in small ways, or uses lower impact materials, the benefits are not just historical, they are modern. That does not mean we can copy Roman concrete everywhere. We cannot simply pour a Roman harbor recipe into every modern bridge. Modern structures have different loads, codes, climates, reinforcements, and schedules, but Roman concrete gives engineers ideas. Use local materials intelligently, design for long-term chemical change. Think about crack repair as part of the material. Do not assume every irregularity is a defect. Let the environment participate when possible. The ancient material becomes a question for the future. What if concrete was designed not only to be strong on day one, but to keep adapting for decades? The word ancient can make technology sound finished. as if everything old belongs behind glass, as if a ruin is only evidence of what people used to know. But Roman concrete shows why that attitude is too small. An ancient wall can still be an active teacher. It can contain chemical structures modern researchers did not expect. It can preserve construction choices that were never written down clearly enough. It can force engineers to ask whether a modern defect is always a defect, whether speed is always the best measure of success, and whether a material should be judged only at the moment it hardens. That last point matters. Modern construction often thinks in deadlines. When can it be poured? When can it carry load? When can the schedule move forward? The Roman examples push attention toward a different timescale. What happens after 10 years, after 100, after salt water has entered every small opening, after storms, heat, pressure, and chemistry have had centuries to work? The strange lesson is that a material can be designed for its future, not only for its beginning. That is not nostalgia. That is engineering humility. There is one more trap to avoid. Respecting Roman concrete does not mean pretending Roman builders understood everything modern science can now explain. They did not know molecular structures in the modern sense. They did not have electron microscopes. They did not write papers about calcium carbonate recrystallization, but they did not need that kind of knowledge to learn from results. If a harbor mix held better, builders noticed. If one ash worked better than another, that knowledge could spread. If quicklime behaved differently in a mix, workers could learn the danger and the advantage. Practical knowledge often arrives before theory. People fermented food before microbiology. They made steel before atomic theory. They made glass before modern materials science. And in the Roman world, builders could make durable concrete before anyone could describe every chemical pathway inside it. That does not make the science less important. It makes the connection more interesting. Ancient craft created the artifact. Modern science explains the mechanism. Together, they make the story complete. A harbor wall is not just chemistry, it is people. Workers burning limestone into lime, crews hauling volcanic ash, hands moving stone and rubble, builders judging moisture by sight and touch, someone deciding when the mixture was ready, someone trusting a recipe because the older builders said it worked. The intelligence of Roman concrete was distributed, not in one genius, not in one secret ingredient. In a whole culture of making, geology mattered, chemistry mattered, labor mattered, memory mattered. That is why calling it a lost recipe is useful, but incomplete. What was lost was not only a formula, it was a relationship with materials, a way of reading ash, lime, water, stone, and time as parts of the same system. Roman concrete was not magic. It was not always better than modern concrete. It was not one secret ingredient hidden by history. It was a material system that sometimes turned weaknesses into strengths. Volcanic ash was not just dust. Seawater was not always just damage. Lime clasts were not necessarily sloppy mistakes. Heat was not just a byproduct. Time was not only decay. In the right system, time became part of the engineering. That is what modern researchers rediscovered. Not that the Romans were secretly modern, but that ancient builders, working without our instruments, learned to make materials that could keep changing after construction. The ruins are not dead stone, they are old experiments still running. And sometimes the future of engineering begins by listening carefully to something that has already survived 2,000 years. If you want another Roman material mystery, watch the Lycurgus Cup next. One story is about concrete that lasted. The other is about glass that changes color. Both remind us that ancient craft can be more sophisticated than it first appears.